Good morning. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. All right, so today, continuing in chapter 11, we're going to take a look at section 11.3, which has to do with something called exponential functions. We have looked at linear functions or linear equations, such as something like y equals 2x, where the graph of which is a straight line. We've looked at second degree or quadratic equations, such as y equals x squared, where the graph is a parabola. Now we're going to be looking at equations in the form y equals, let's say, 2 to the x power, where the exponent is the variable. So y equals 2 to the x power is an exponential equation. And I'm going to pause the recording and switch screens, and we're going to look at some graphs of those things. So, all right. So let's take a look at the equation y equals 2 to the x power. Actually, you know what? I'm going to change that. I'm going to use black instead because it shows up better, at least for now. So y equals 2 raised to the x power. And I'm going to make a table where x is going to go from -3 to +3. So if x is -3, y equals 2 to the -3 power. Recall that we can rewrite a base to a negative exponent as 1 over that base to a positive exponent. 1 over 2 cubed is 1 over 8. If x is -2, y equals 2 to the -2 power, 1 over 2 squared, or 1/4. If x equals -1, y equals 2 to the -1 power, or 1 over 2 to the 1, or 1/2. If x is 0, y equals 2 to the 0 power. Recall that any base other than 0 raised to the 0 power equals 1. If x is 1, y equals 2 to the 1 power, which is 2. If x is 2, y equals 2 squared, which is 4. And if x equals 3, y equals 2 cubed, which is 8. So let's plot those points and see what we get. If x is -3 and y is 1/8, that's right about there. -2, we're up to 1/4. -1, we're up to about 1/2. At 0, we're at 1, 1, 2, 2, 4, and 3, 8. So we get this graph. Let's see if I can draw it here. Okay, so there's the graph of y equals 2 to the x power. It sort of looks like half of a parabola, only it doesn't. On the right side it does. It keeps climbing as it goes to the right, but on the left side it keeps getting smaller and smaller and smaller, but it never touches the x-axis. Because notice on our table over here, okay, going up, x keeps doubling. Going down, x keeps getting cut in half. Half of an 1/8 would be a 1/16, and a 32nd, a 64th, a 1/28, a 256, blah, blah, blah. So it's never going to reach 0, but it's going to get closer and closer to 0. All right. What is the domain of this thing? The domain would be all real numbers. X goes to -infinity, x goes to +infinity. The range would be y has to be greater than 0, okay? There's no x-intercepts, and the y-intercept is at, what, 0, 1. Also, we would say that this equation or function is increasing over its entire domain. As x gets larger, y gets larger, and continues in that situation. Okay, now let's say we look at the graph of y equals 3 to the x. What's that going to look like? All right. And so y equals 3 to the x. Okay, and then we'll make our table, and we're still going to use -3 to +3 for the x values. So if x is -3, y equals 3 to the -3 power, which is 1 over 3 cubed, which is 1/27th. If, let's see, if x is -2, y equals 3 to the -2 power, which is 1 over 3 squared, which is 1/9. If x is -1, y equals 3 to the -1 power, which is 1 over 3 to the 1, or 1/3. If x is 0, y equals 3 to the 0 power, which is 1. If x is 1, y equals 3 to the 1, which is 3. If x is 2, y equals 3 squared, which is 9. If x is 3, y equals 3 cubed, which is 27. So let's graph those table values in red. -3 is 1/27th. -2 is 1/9. -1 is 1/3. Again, I'm kind of approximating here. But at 0, we're at 1, 1, 3, 2, 9, and then 3/27 is off the graph. Okay. So let's look at the characteristics of the red graph. The domain is all real numbers. The range is greater than 0. There's no x-intercepts, and the y-intercept is 0, 1. And it's increasing over its entire domain. Okay, so everything kind of looks the same there, doesn't it? Except it grows faster. These are doubling, these are tripling. All right, let's go back and let's look at yet another graph. And this time, we're going to go with, let's see, let's go with blue. Okay, y equals 1/2 to the x power. And again, I'm going to use the same table values. X, y, -3, -2, -1, 0, 1, 2, and 3. All right. So if x is -3, I'm going to write these down here. Y equals 1/2 to the -3 power, which would be 2 over 1 to the +3 power, or 2 cubed, or 8. If x is -2, y equals 1/2 to the -2 power, which is 2 over 1 to the +2 power, or 2 to the +2 power, or 4. If x is -1, y equals 1/2 to the -1 power, which is 2 over 1 to the 1 power, which is 2. If x is 0, y equals 1/2 to the 0 power, which is 1. If x is 1, 1/2 to the 1 power is 1/2. If x is 2, 1/2 squared would be 1/4, and finally 1/8. All right. So whereas over here, for the black equation, things were doubling. For the blue equation, things are halving, so to speak, because the base is a half. So what would that graph look like? -3, 8, -2, 4, -1, 2, 0, 1, 1/2, and then a 4th, and then an 8th. Oops, shaky hands there. Well, the blue graph, the domain's all real numbers. The range is greater than 0. There's no x-intercepts. The y-intercept is at 0, 1. But it's not increasing. What's it doing? It's decreasing. Okay. So if the base is larger than 1, we get an increasing function. If the base is smaller than 1, we get a decreasing function. What if the base, well, and hang on though, smaller than 1, but still positive. So if it's smaller than 1, but greater than 0, okay? Now, what if the base is 1? What does that look like? Okay, well, let's see here. The base is 1. Let's make this one green. Y equals 1 to the x power. -3, -2, -1, 0, 1, 2, 3. Well, let's see. If x is -3, y equals 1 to the -3, which is 1 over 1 cubed, which is 1 over 1, which is 1. If x is -2, y equals 1 to the -2 power, which is 1 over 1 squared, which is 1 over 1, which is 1, 1, 1, 1, 1, 1. And we get this graph. Well, that doesn't look like an exponential function. That looks like a constant function, a linear function. So basically, we say that the base can't equal 1. Okay. Now, what if the base is negative? What happens then? Let's go back to red. Okay. Y equals, how about -2 to the x? Now, don't confuse that with this. Here the base is 2. We're talking about where the base is -2. So y equals -2 to the -3 power would be 1 over -2 to the 3rd power, which is 1 over -8, or -1/8. Okay, so -3, -1/8. We're down there. If x is -2, y equals -2 to the -2 power, which is 1 over -2 to the +2 power, which is 1 over 4, which is there. If x is -1, y equals -2 to the -1, which is 1 over -2 to the 1, which is -1/2, which is, let's see, here. And then if x is 0, -2 to the, that's going to be 1, -2, 4, -8. The problem is this thing's going to jump all over the place. It doesn't work. In fact, if you put it on a graphing calculator, it just sits there and spins. So what we get are the following things, okay? If we have an exponential function in the form of y equals b to the x, the base has to be greater than 0. The base cannot equal 1. If the base is greater than 1, we get a graph that is increasing over its entire domain. If the base is less than 1 but greater than 0, we get a graph where the that's decreasing over its entire domain. Forgot what I was going to say there. All right. In all these cases, there's a y-intercept at 0, 1 and no x-intercepts. All right. Now, what if we come in and we do things to it? What if we, let's say we've got y equals 2 to the x. Actually, let's go back. Y equals 2 to the x, which is this black graph here. Okay, that first one. Let's see if I can wipe everything else out of there without making too big of a mess. I got rid of the black graph. Oh, well, hey, what? We'll go to the next page. Let's see. It's going to be here and here and here and there and there and there and there. Okay. So there is the graph of y equals 2 to the x. What do you think y equals 2 to the x plus 4 would look like. We had a constant over to the right. Remember what happened with a parabola, like y equals x squared and then x squared plus 4, it went up 4. So this would move everything up 4 units. So it would look like that kind of thing. And that's not super accurate. I'm just trying to get this, give you the rough idea. What about y equals 2 to the x minus 3? That would go down 3 units. What about y equals 2 to the x? And then we put a minus 1, only it's part of the exponent. So it's not a constant outside. Well, on the inside, it does the inverse. So a minus 1 would move the graph that way 1 unit. A plus 3 would move the graph negative 3 units. Okay. What about a negative in front of it? Okay. Now it's not negative 2 to the x, it's negative 2 to the x. That's going to flip this thing over. Okay. So all those flips and shifts and reflections and things that happen with parabolas also apply to exponential graphs as well. All right. Now I want to stop. Now let's take a look at some application problems involving exponential functions or exponential equations. So we've got this following equation. A equals 500 times 2/3 to the t power. So this part of the equation is the exponential part. That 500 out front is sort of a multiplier or almost like a coefficient, but it's not part of that base that's being raised to the power. Okay. Well, without even reading the story problem, which I'm going to do in a minute, there's some things we can tell about this equation. First of all, let's say that t stands for time. Well, when t equals 0, what's 2/3 to the 0 power? That's 1. What's 500 times 1? That's 500. So what that says is that if this equation, if t stands for time, at the beginning of time, there are 500 of something. Okay. What's happening to those 500? Are they getting larger, smaller, staying the same? Well, 2/3 to the t power, since the base is between 0 and 1, it's going to decrease. So what we've got here is a population of 500 of something, and over time, they're going to decrease. Let's read the problem and see what it says. It says 500 grams of a radioactive material, so there's our starting value, decays, it's decreasing, according to the formula A equals 500 times 2/3 to the t power, where t is measured in years. Find the amount present in 10 years. So A equals 500 times 2/3 to the 10th power. Round to the nearest 1/10 of a gram. So is it going to increase or decrease? It should decrease, right? So we've got 500 times, parentheses, 2/3 raised to the 10th power. And we get 8.67076495 on and on. And let's see here, it says round to the nearest 10th of a gram. So this is the 10th, the 7 would round up. So we've got approximately 8.7 grams. Okay, so the substance over 10 years decayed considerably, didn't it? All right. Another example, the population of North Rivers, actually, let's look at the equation first before we read the story. Again, if t is time, at the beginning of time, what's the population? 3745, right? Because if t is 0, 0.93 to the 0 power is 1. 1 times 3745 is 3745. Is this thing growing or decaying? It's decaying. By what percent is it decaying per year? Well, if each time t increases by 1, we get 93%, 0.93 of what we had before. That's a loss of 7%, right? So whatever is happening, it's decreasing at a rate of 7% per year. All right, let's read the problem. The population of North Rivers is decreasing exponentially according to the formula, where t is measured in years from the present date. Find the population in 6 years, 9 months. Well, if t equals years, 6 years, 9 months. 9 months is 9/12 or 3/4 of a year, so 0.75 years. So 6 years, 9 months would be 6.75 years. So P equals 3745. Once again, I write too fast and it gets too sloppy. 3745.93 to the 6.75 power. 3745 parentheses 0.93 close parentheses raised to the 6.75 power. And we get 2294.62502 rounding to the nearest person, 229. Let's see, that would round up. So the population would be 2,295. Okay. All right, now here's a compound interest problem. Compound interest problem. There's a formula that involves compound interest, and it looks like this. Okay, where P is the principal or the initial amount invested, R is the annual interest rate, T is time in years, and K is the number of compoundings per year. Now, what do I mean by that? Well, simple interest, you put money in the bank and it sits there, and at the end of the year, they give you, let's say it's 3%, they give you 3% of what you had invested. Compound interest, when they calculate the interest, they put the interest in the account, and that now becomes part of the principal, so it gets interest. So you get interest on the interest, and then you get interest on the interest on the interest, et cetera, et cetera. K is the number of times per year that they compound the interest. If it's annually, K is 1. If it's semi-annually, K is 2. If it's quarterly, K is 4. Monthly, K is 12. I guess I'd have to hold up some toes. Daily, 365, etc., etc. Okay, so using this formula, A equals P times 1 plus R over K to the KT power, we have the following scenario. An initial deposit of $10,000, so that's P, earns 8% interest, so that's R, which we're going to write as a decimal number. Compounded quarterly, so K is 4. How much will be in the account? So that's the accumulated amount. We don't know that yet. After 10 years. Okay. So A equals $10,000 times 1 plus 0.08 over 4 to the 4 times 10 power. All right, now I can put this all into my calculator just as it is, or I can simplify some things sometimes. For instance, 4 times 10 is 40. There's no doubt about that. 0.08 divided by 4 comes out to be 0.02. That works out nicely. But if, let's say you try to simplify one of these things and it doesn't come out nicely, it's got a repeating decimal or something, then back up and leave it as the exact numbers that were there in the first place, punch it all in at once. Don't round off ahead of time. Okay, so I'm going to put all this in the calculator just like it is. So I've got 10,000 times parentheses 1 plus 0.08 divided by 4 close parentheses. Then I'm going to use the little caret key raised to the power parentheses 4 times 10 close parentheses, and I get 2208.0 39664. All right, this is money, so we're going to round to the nearest cent. So the 6 would round up, and we're going to end up with $22,080.40 because the 6 rounds up, turning the 9 into a 10, kicking the 1 over to the 3, making it a 4. All right. Let's look at another example. Comparing interest rates. How much more interest would $1,000 earn in 5 years, compounded quarterly, if the annual interest rate were 5.5% instead of 5%? Okay, so we've got our formula. And let's see, P and R and K and T and P and R and K and T. We've got, let's see, $1,000 in both cases. We've got an annual interest rate of 5%, which is 0.05, or 5.5%, which would be 5.5%, or 0.055, compounded quarterly and 5 years. Okay, so initial investment's the same, the time's the same, the number of compounding is the same, but the interest rate in one scenario is 5%, and second scenario 5.5 or 5.5%. So let's see what the difference is by increasing the interest rate by 0.5%. All right. So the first one, A equals $1,000 times 1 plus 0.05 over 4 raised to the 4 times 5 power. 1,000 times parentheses 1 plus 0.05 divided by 4, close parentheses, little caret power key, parentheses 4 times 5, close it up, equals, I get, let's see, 1282.037, so that would round up to 1282.04. Okay, so 5% you'd have $1,282.04. Now let's go back and do the second one, where A equals 1,000 times 1 plus 0.055 over 4 raised to the 4 times 5 power. 1,000 times 1 plus 0.055 divided by 4, close it up, raised to the power, parentheses 4 times 5, close it up, and I get, what, 1314.066. The 6 here is going to round up, so 1314.07. And it said how much, let's see, how much more interest would you get? Okay, so we're going to take 1314.07 minus 1282.04, and we get $32.03. So same amount of money invested, same amount of time, same amount of compoundings, but by having the interest rate 0.5% higher over that 5-year period, we make $32.03 more, which may not seem like a lot, but I mean, it's better than not getting it, right? Okay, now let's say that $1 was invested on July 4th, 1776. So $1 invested at 5% interest, compounded annually. What would it be worth July 4th, 2076? All right, so from 1776 to 2076, again, July 4th, would be 300 years. Okay, so A equals $1 times 1 plus 0.05 over 1 raised to the 1 times 300 power. A equals $1 times, well, 0.05 divided by 1 is just 0.05, and plus 1, we get that. And 1 times 300 is that, right? So if we take 1 times parentheses 1.05 raised to the power 300, we get 227,3996.129. Rounding the 9 up, $2,273,996.13. So, don't you wish you'd invested $1 at 5% back then? All righty, that's it for today. Just a reminder, I will not be in my office hour this afternoon. So if you have any questions, email me, and after my meeting, I will check and see if anybody has questions. Otherwise, I'll see you tomorrow. So take care.